Hello class, welcome back. This is lecture 8. Today we're talking about telescoping series and the divergence test. So telescoping series are just another type of series that we can identify pretty quickly like we could with geometric series. It's a little bit harder, but you'll see. Okay, so here's the idea behind telescoping series. So sometimes the terms in a series cancel out previous terms or future terms. And remember, we need to know what the partial sums look like, and this will let us do it. This lets us write a nice formula for SK. Okay, so let's just see an example. Because these ones, there's not like a typical form like there was for geometric. It was a number to the nth power. So this one doesn't have a typical form, but it's usually pretty easy to spot once you start writing out some terms. So here's a good example: 1 over n minus 1 over n plus 1. So at first glance, what you might see is this guy and think like, oh, I know this. Didn't this thing diverge a long time ago? And it does. So does this guy actually. But just because they both diverge doesn't mean I can say anything about this from that information. It's not like when they both converge, then you can distribute the summation and do them independently. But when they diverge, you can't do that. So we actually just have to deal with it as it is. And the way to notice it's a telescoping series is to just write out some terms. So let's just plug in some numbers. So if I plug in 1, I get that. And then I add. So really this is like A1. All right, and then I add and I get A2. So now I plug in 2. And then I add and I plug in 3. And so on like that. So the idea is that if you write them out and you simplify a little bit, you start to notice some cancellation that seems to, oh wait, sorry, this should be a 1 over 2. That seems to occur. So like these two seem to cancel, these two seem to cancel. And then like the next ones seem like they would all cancel. But to really do this, we need to know the partial sum. So what we do is we just think about the partial sum up to k and stop there, and then we take the limit. So it's going to look just like what I just did, except I stop at the kth term. So the last thing I'm going to do is plug in k, and that'll be the last term. And now because it's finite, I can actually cancel properly. So I can say these cancel. This one will cancel with the next thing in there. This guy will cancel with the previous one in there in the ellipses. So what's really going to be left is just the first term that didn't have anything to cancel with, and this term didn't have anything to cancel with. So you just get this. And so this is a formula for the partial sums. So now we can take the limit of the partial sums to get the actual sum of the series. Oops. So it's the limit of this thing. And as k goes to infinity, what happens here? Well, the the denominator of a fraction is growing very, very big, going to infinity, so it makes the fraction go to 0. So you just get 1 minus 0 is 1. So this guy does converge. And it converges to 1. So it's a bit weird because independently, these both would have diverged if you just looked at the two independently, but subtracting them, you get something that converges instead. Okay, so in general, the reason it's called a telescoping series is because like this big expansion just shrinks because all the middle things cancel out. So that's how you know you're in a telescoping situation. So let's do another example where this happens. You pretty much have to have a minus for this to be happening. So it usually looks like something minus something that's the next one, or maybe the previous one. You can do it the other way too. So something like this is telescoping because when you write out the partial sums, so let's go up to k again. So cosine of 1 over 1 minus cosine of 1 over 2. That's the first term, that's a1, plus, now plug in 2 cosine of 1 over 2 minus cosine of 1 over 3. That's the second term, a2. Go all the way up to the kth term. So cosine of 1 over k minus cosine of 1 over k plus 1. And same exact situation. These are going to cancel in the middle again. And so you just get cosine of 1 minus cosine of 1 over k plus 1. And then you take the limit as k goes to infinity. And what happens here? Well, the first guy doesn't have any k in it. So it's just a number. Cosine of 1 is just some weird number. And then over here, as k goes to infinity, this guy gets really, really big, makes this fraction get really, really small and go to 0. So this is really just cosine of 0. Cosine of 0, we can say what that is. That's 1. So then this is the final answer. Cosine of 1 is not something, it's not from the unit circle, so you wouldn't know what that is. Okay, let's do one more. And so hopefully you can see the pattern. They all sort of look the same with just slight variations. So e to the 1 over n minus e to the 1 over n plus 1. Very similar. It's telescoping again, because when you do the partial sum up to k, you notice that everything cancels in the middle. So e to the 1 over 1 minus e to the 1 over 2. That's your first term. Add, plug in 2, e to the 1 over 2 minus e to the 1 over 3. So on like that until you get to the kth term. And same exact thing happens. All the middle guys cancel with something because there's a positive and a negative version of each thing. But the first and the last one do not. So then you can take the limit again. And what do we get here? Well, e to the 1 is just e to the 1. This guy, same idea. So this is going to go to 0. So it's going to be e to the 1, which is just e, minus e to the 0, which is 1. And so you get that. Okay, so you can see that there's very distinct form for these guys. So we have two types now that we can sort of break things into. We have geometric, which look like look like a number to the nth power, and you can explicitly calculate the sum using this formula, and there might be an extra number here sometimes that you call C, but then you would just multiply by C. So if it looks like that, you can do it. If it's telescoping, then you can take the limit of the partial sum to figure out the answer of whatever it is. It doesn't have to start at 1, or I just happened to start these ones at 1, but it started at something else. The point is that if it's telescoping, you can just do the limit. But lots of series are too complicated. So we're going to learn lots of other tricks. So they're too complicated to just find SK, the partial sums, and do the limit. So we don't. We'd like think of other tricks that will help us instead. Okay, and here's the first trick. So we learn tricks to determine divergence or convergence of a series without calculating SK. So we just avoid it completely. Okay, so here's the first trick. It's called the divergence test. So based on the name, you should be able to guess what it does. It tells you immediately if a series diverges. So you can never use it to show convergence. Keep that in mind. If you ever use this thing to show convergence, if you ever say blank converges by the divergence test, then that's way off. You're going to get a big 0 because it just cannot happen. Okay, so what is this test? If series doesn't have to start at 1, I just got to pick a number. But if a series has the property that if you just take the limit of the sequence instead, so you just take those terms and you just immediately take the limit. So you don't even bother adding, you don't do any partial sums, you just take the limit. And if it equals a number besides 0, or if it doesn't exist, then you can immediately say that the series diverges. So what's the intuition? Well, the intuition is if these guys don't even shrink to 0, then there's no way that when you add them up, they could possibly add up to a finite number because they're not shrinking to 0. So then you're just going to be adding a bunch of like whole numbers or something that just add up more and more and add up to infinity. So that's the idea. So keep that in mind. Okay, so the terms, the AN terms, need to shrink to 0 for the sequence to possibly converge. But even that's not enough, as we'll see. But it's definitely necessary. Okay. And the other big warning, like I said before I wrote the test, you can only show, it only shows that a series diverges or it's inconclusive. Those are your only two options. Okay, never will it ever show that a series converges. Okay, so we'll do a couple of examples to see how these things work. All right, so here's the first one. So the divergence test is like the one that you hope will work because it's the easiest, and you do it first. But it usually doesn't work. It only works when we're in this section because it gets a little harder. Problems get harder, and it just doesn't work later. Okay, so here's the idea for the divergence test in an example. So I just say, okay, forget adding anything up. I'm just going to take the limit instead of the series. I'm just going to take the limit. And then do I know how to do that? Yes, I do. You would change it to, if you want to be very official, change to x, and then you do L'Hopital's rule, and you end up with 3/5. And then you say, is this number 0? Well, let me ask you, is 3/5 0? No, it's not 0. So if you get something that's not 0, then the idea is that these do not shrink to 0, these terms. So when I add them up, there's no way it could add up to a finite number. It's going to be too big. It's going to add up to infinity. So that's what the divergence test says. So that means immediately we can say that this guy diverges. Diverges by the divergence test. If you want to be official, that's how you would say it. Okay, let's do another example where the divergence test does not work. So this guy, we do know it diverges, but that's because we did it the long way a long time ago. The divergence test is not going to help us here. All right, so we can try the divergence test. Never hurts to try, even if it doesn't work. So the divergence test says, okay, take the limit as n goes to infinity of the series of just the sequence. So you forget the series exists. You just do that, and you say, okay, what is this? Well, because there's an n on the bottom and no n's on top, it just shrinks and shrinks and shrinks to 0. And you say, is this 0? Whoops, it is 0. So yes, it is 0. Okay. So what do you get to conclude? The answer is nothing. So you can just say that the divergence test, if you really want to say something, you would just say the divergence test is inconclusive. Okay, so just because it goes to 0, just because this happens, doesn't mean that this converges. So this goes to 0 does not mean that this guy converges or anything. It could do either. You basically have to do something else. So you must try something else. In this case, we did this problem a long time ago. So what we would do, if this was like from scratch, we would do a different test or something. It does turn out to diverge. So it's a perfect example of, even though the sequence terms go to 0, even though these go to 0, that does not necessarily mean that the series will converge. Okay, so we showed this a long time ago. We showed this. Sort of a long problem, but we did it. Okay. Let's do another one. E to the 1 over n squared. Okay, so you see, like, okay, are these guys shrinking to 0? If not, then it's going to diverge automatically just because the terms are not getting small. They need to get small. They need to go to 0 in order for you to be adding up things, infinitely many things, and not getting infinity. Okay, so what's this limit? Well, as n gets really big, that guy goes to 0. So this is 1. So is this 0? No, it's not. So you say that the series, you can say the series diverges by the divergence test. Oops. So it's the divergence test is the easiest one to use because you just take the limit. But the limit, I'll have to reinforce this a million times because everyone gets this mixed up. These two things are not the same. Not the same thing. Right? This one is just where is the list heading or something like that. Where are the numbers going towards? And they're going towards 1. This is what do they add up to? And in this case, they don't add up to any number. They just grow infinitely big. And that's because the terms go to 1. So it's as if you're just adding a bunch of 1s up together. And if you just add up a bunch of 1s, then of course that's going to add up to infinity. It's going to be too big. You need to add up tinier and tinier numbers for it to not go to infinity. Okay, so I just want to keep re-emphasizing this point because such a common mistake. So given a series, so let's keep it a bit general right now. The idea is that you absolutely need the limit of the terms to shrink to 0 in order for the series to even have a chance of converging. Might still not converge, but it needs to have that in order for it to even have a chance to maybe converge, because otherwise you'll be adding up numbers that are too big. Okay, but however, on the flip side, just because the limit is 0, this does not mean, it means nothing. It means that you don't know anything about the series. It does not mean that this guy converges. And we have the best example possible, which is this one. This thing actually diverges, even though the limit of the sequence is 0. Okay, so why does that happen? So this is because the terms, you could think about like 1 over n, they shrink too slowly. They don't shrink fast enough. Okay, so let's do 3 more real quick examples here. So here, 1 over n squared, you take the limit of just the inside and it's still going to be 0. So the divergence test is inconclusive. Okay, it tells you nothing about the series. You're always trying to figure out something about the series by doing something. And here we're learning about the series by taking the limit of the sequence. In this case, we're learning nothing at all. It doesn't help at all. So we'll have to learn something else to deal with that. That's just the end of that problem now, because we don't know how to do it. So what about this one? Cosine of 1 over n squared. If I take the limit of the inside, then this becomes cosine of 0 because the n squared gets really big and makes a tiny fraction. So the inside goes to 0. Cosine of 0 is 1. So this guy diverges for sure because the limit is not 0. And it diverges by the divergence test. Done. We've said if I forget about the series and I just think about the sequence, then those terms don't even go to 0. So when I add them up, they're for sure going to add up to be too big. They're not going to be finite. And that's that. Whoops, last one. I guess I'll use a different color. 3n over 10n minus 1. So the divergence test, again, you just take the limit of the inside. Oops. And so you get 3 over 10 using L'Hopital's rule, because the powers of n are the same. So you can say that this guy diverges by the divergence test. Oops, I keep doing that, sorry. Okay. Right, so you didn't get 1, you didn't get 0. So that's enough information to immediately say something about the series. So in all of these future problems, what we're doing is we're trying to understand the series, and we're just using tools to do that. And in this divergence test, the tool is just look at the sequence and see if the sequence goes to 0 or not. If it does not go to 0, great. You can say something like here. You could say something about the series. You can say it diverges by the divergence test. If it does go to 0, like here, that's too bad. You can't say anything about the series. Again, you're looking at the sequence to understand the series. Subtle difference. These two things are not the same thing. Okay. So I hope I've repeated myself about that enough, because it's a very common mistake where people just treat these two things as the exact same thing, but they are not the same thing. One is a sum, one is a series. The sum, you're trying to find out what it adds up to. The other is just a limit, and you're just trying to see what the numbers are going towards, but you're not adding or anything like that. Okay, so that's it for today. See you next time.